Good morning, everyone, and welcome to the webinar. My name is Caroline Stewart, and I work in the marketing team at Crate.io. I'm joined today by Tanay Pant, who is your presenter on the webinar today, and he'll be taking you through the grand quadrant of powerful databases. Before I hand over to Tanay, I'm just going to go through a few housekeeping items. If you have any problems with the sound or you can't see the screen, please let us know through the chat window. We'll take Q&A at the end of the presentation, but if you do have a question, please feel free to pop it in the questions box that you'll see on the screen. And finally, we will be recording the session, and we will send this out to you through email within the next few days. So, without further ado, I'd like to hand over to Tanay. Thank you.
Thanks, Caroline, and hello, everyone. Welcome to today's webinar on the grand quadrant of powerful databases. I'm really happy to see all of you here. So today we will discuss a number of topics, which include time series data and its different use cases, relationship between sensors and time series data, so as to get a context of the quadrant itself. Then we'll talk about the grand quadrant of powerful IoT databases, the CrayDB ecosystem, and finally, we will go through some technical and functional comparisons of CrateDB with some popular databases. My name is Tanay Pant, and I currently work as a developer advocate at Crate.io in Berlin, and I really enjoy working with time series and sensor data. I'm also a tech speaker for Mozilla and volunteer to their various projects in my spare time. I've published books on Firefox OS, building a virtual assistant on Raspberry Pi, and web-based virtual reality. I'm also an software innovator in the field of IoT, and towards the end of this webinar, I will share my email and Twitter handle. So if you have any questions after the event or have any interesting project ideas, feel free to reach out to me. I'd be really happy to collaborate. All right, so let's get started. So I'm not sure if everybody present here with us today is familiar with the concept of time series data. So I'd like to give you a super brief introduction to that first. So what is time series data? And most importantly, how does it differ from other forms of data? So to imagine this, think about a sensor. And this sensor is sending streams of data over a period of time. And if you were to plot this data, one of the axes would be time. So as compared to some other workloads, this data is not added as an update to the database. But if you think of a platform like WhatsApp or Facebook, each time you set a new status, it rewrites your previous one, as this change is made as an update to the database. Now, time series data is added as an insert, and this is the primary way of adding time series data to a time series database. And time series databases introduce efficiencies by treating time as a first-class citizen. Having such a rich amount of historical data allows you to delve into various aspects of your operation, such as analyzing the past, monitoring the present, or even predicting the future. For instance, this graph denotes time series data as we are measuring metrics such as temperature and pressure against time. Here again, we have another example of time series data as we are measuring the downtime hours of two factories, one based in New York and one based in Florida against months, which is essentially time. Now, if you take an abstract look at the use cases of time series and the kind of data generated, you can roughly characterize them into two types. First of all, we have IT and system monitoring. So this can be termed as the traditional use case of time series databases. So if you talk about the characteristics of this particular use case, you can say they have tens of hundreds of metrics or sensors, real-time write functionality, rarity of complex queries, and data volumes that usually fall in gigabytes. And if you talk about the different databases that are being popularly used in this segment, InfluxDB is an excellent example as a database for this category. And then we have industrial sensor data. So this is an emerging sector that I feel has not been talked about enough. This is characterized through hundreds of thousands of metrics or sensors, real-time queries that are under highly concurrent load and must access gigabytes to hundreds of terabytes of data. So CrayDB is an especially good fit for this category. And there are also some other characteristics that separate the two use cases, like projects that fall under the first category tend to be internal IT services, and the data in the database or monitoring are often not that mission critical. And the projects that fall in the latter category are often mission critical, transformative, and enable real-time data-driven decision systems in factories or really critical systems. Now, industries all around the world have been working with a number of different solutions to transform the way their manufacturing processes work. And these systems aim to control and provide real-time feedback by recording data from different sensors, motors, and valves. And all this data that is gathered contains multiple values and parameters along with a timestamp, which we learned earlier makes this essentially time series data. And the complex time series data coming in is coming in at really high speeds. And it also needs to be queried in real time. And hence this data is sent to a time series database like CrateDB and monitored visually via a dashboard like Grafana, Power BI, or even Apache Supersets. And if you take a look at the last decade, you can say that it's a machine data world. And machine data means explosive growth. So in 2018, we saw a boom in the number of IoT devices and their use cases. There was an increase in the use of IoT and sensors in different contexts, such as smart factories and smart cities. And we learned about how databases like these can help in these contexts. The total number of IoT devices is moving towards 20 billion by the year 2020, and every second, another 127 devices are being connected to the internet. Just for an example, take a Boeing 787, which generates half a terabyte of data during a single flight. And if we talk about, let's say, plastic manufacturing industry, there's a wide array of data being produced per each bottle that is manufactured. And then there's data per each production line with about as much as 10 production lines per plant. And this data is being generated by around 950 different sensor types. And that's just one factory. This particular company has 180 factories in 45 different countries. That means data on billions of bottles. There's a good chance that the bottles that you use in your fridge have been running its data through the Crate platform during their production cycle. If you'd like to know more about this specific use case, feel free to check out our blog where we have a detailed article on how we work with Alpla. And in case you'd like to check out a demo of that, please visit my previous webinar on Industry 4.0. Now, we will be using a graph to define the market's most efficient and most scalable databases in terms of resource effectiveness, hardware costs, productivity, write and read power. But before continuing on with the placement of various databases, let's define the criteria that we'll use to assign these databases their position in the graph. So these criteria will also help you to unveil the business value of these databases and assist you in making a focused and clear decision about which one serves your use case in the best possible manner. And another thing, very important thing to note here is that there is a context to this quadrant and the placement of the databases. So this quadrant works in the context of IoT, machine data, and digital industry, basically the use cases that we just talked about. So first of all, we have efficiency on the y-axis. Efficiency helps you in achieving resource effectiveness, which essentially means less hardware costs, and the learning curve required to operate and deploy the solutions to production is not steep, which results in increased developer productivity. And it also results in lesser oversight and administrative time, which is also less for these kind of databases. Then we have scalability on the x-axis. Scalability is an exceedingly important factor in this age of data explosion, especially since we talked about how many number of IoT devices are coming online with high data ingestion rates. It is important that the databases maintain their power and the ability to perform queries in real time, especially with systems that call for a high degree of concurrency. I'm proud to present before you the industry's first IoT database quadrant. When it comes to define the market's most efficient and most scalable database in terms of resource effectiveness, you will find only CrayDB is at the right spot. In the grand quadrant of efficiency and scalability, CrayDB is at the most significant position for both attributes. Compared to Elastic, which is really close to Cray's efficiency and scalability status, CrayDB delivers more efficiency. Compared to Cassandra, which shows much more scalability, CrayDB shows far more efficiency. We shall go a bit deeper into the technical and functional comparisons of some of the leading databases against CrayDB in a while. But first, let's talk about CrayDB itself and what makes it a giant in this realm of databases. At CrateDB, we've been working on developing technical architecture in IoT and time series field for over the past 5 years. We have a co-selling agreement with Microsoft, and our client portfolio includes companies like McAfee, Nokia, Rauch, Alpla, and many more. Earlier this year, CrateDB was also named a Cool Vendor in the Gartner 2019 Cool Vendors in Manufacturing Operations report. So to learn more about the CrayDB ecosystem, let's start off by going into the heart of the honeycomb to the core technology and talk about CrayDB and what makes it stand apart from the various other databases in this segment. So CrayDB is a new kind of distributed SQL database that is best suited for handling industrial time series data due to its ease of use and ability to work with many terabytes of time series data with thousands of sensor data structures. CrayDB is quite simple to install. You can spawn an instance of CrayDB with a single line on your terminal or on Docker. CrayDB uniquely combines standard SQL with NoSQL benefits, so it operates on a shared nothing architecture. Various nodes in a cluster coordinate seamlessly with each other, and the execution of write and query operations are automatically distributed across the nodes in the cluster. Some other salient features of CrayDB include that it is NSI SQL compatible, including joins and Postgres via protocol, which makes integration with tools such as Grafana really easy and prevents lock-in. CrayDB also supports distributed SQL with full-text search, JSON, time series data, geospatial data, and even blob tables. This architecture is quite well suited to containerization, meaning a cluster running on Kubernetes can be scaled up or down very easily. Sharding, replication, and rebalancing of data as the cluster size changes are automated. And until recently, workloads like these often required a NoSQL solution like Cassandra, Elasticsearch, or InfluxDB, often in combination with a traditional relational database. So CrayDB makes it possible to handle them in a single system without sacrificing the familiarity and power of SQL. So this fire hose of complex data that's produced by the various use cases that we talked about needs to be handled in real time. And in order to take real-time actions on the factory floor, we need something, CrayDB running on something really strong. So let's now talk about the next layer of the honeycomb built on the core CrayDB technology, which is CrayDB Cloud, also known as CrayDB on Azure. So CrayDB Cloud is a scalable SQL service hosted on Azure and operated 24/7 by the experts at Crate.io. So it's ideal for industrial time series processing and other IoT and machine data analytic workloads. So it has real-time query performance for partitioning, parallel processing, and in-memory columnar indexes, which enables real-time complex analytics and AI, not just simple time series aggregates. And it also has a really amazing Azure IoT integration via built-in interfaces to Azure IoT Hub, MQTT, Postgres via protocol, JDBC, REST, and also a native .NET Core driver. You can also take everything that we talked about and move it to the edge, and it is as simple as deploying a few modules on Azure IoT Edge. So because of the sheer volume of the data that is generated, it is quite possible that at times customers like smart factories would like to store the data on Edge for reducing network overhead and latency so that they can take the actions on the factory floor with an even shorter turnaround time. We recently collaborated on a demo which shows just how to do that. So this sample is hosted on GitHub. Feel free to check it out. It's under github.com/crate and shows how to store machine data from OPC UA servers locally in a single node CrateDB database. All necessary components here will be deployed by the Azure IoT Edge. And we are using these IoT modules that are mentioned here. So first of all, we have OPC UA server simulation module. So after that, we have OPC UA publisher module. And you would not be using the server simulation module if you are connecting it to a real OPC UA device, of course. Then we have a CrateDB module, a CrateDB saver module, which basically pushes the published data to CrateDB, an enrichment module that reads data from the raw table. So oftentimes the data that is coming in might be unstructured, or it might be structured data with a lot of different messages. So this basically takes data from the raw table, enrichment module takes data from the raw table and makes it strongly typed and puts it into different rows. And it writes it to the metric table. And finally, the Grafana module for visualization of this data, which is reading it from the metric table. So if you take a look at the repository, you can use Vagrant to simulate an edge device. And first of all, the OPC UA data comes in, which is basically machine data. The enrichment module takes this data, enriches in a way similar to what we just talked about, Enriched data is stored in a metric table, and after that, we can visualize this data using Grafana IoT Edge module. And it's quite easy to connect CrayDB to that because of the Postgres wire. Now the time series data can be visualized on a dashboard in Grafana. We presented this demo at Microsoft Inspire this year, and in case you are around Frankfurt, we will also be presenting that in IoT in Action event. So if you're there, feel free to drop by, and I'd love to show this all to you. Now let's take a look at how CrayDB compares with some popular or some traditional databases. So a while back, we put together a benchmark that compares CrayDB versus PostgreSQL query performance. The results of this benchmark show that CrayDB performs significantly better than PostgreSQL with actions like selects, aggregations, and grouping. So this test simulates an application that collects sensor readings from separate customer sites and stores them in a multi-tenant database. So this is a really common use case, a SaaS application that enables customers to monitor sensor data via real-time dashboards. So this data set contains 314 million records and simulates sensor readings gathered over a period of 1 year. Each record contains a lot of information about the sensor and sensor readings. So it basically has a UUID, a universally unique identifier for the sensor reading, a timestamp, of course, the ID of the customer tenant from which the sensor is reporting, ID of sensor, type of sensor, 2 sensor readings in the form of an integer, 2 in the form of a floating time number, and 1 in the form of a Boolean data type. And finally, a generated column that contains the week of the timestamp for indexing or partitioning purposes. All right, so this is our data set. With this data, we benchmarked a scenario that is common when dealing with large amounts of numerical sensor data, which is aggregations. Now, aggregations like averaging and totaling are everyday queries that are quite useful in real-time analysis of sensor data. The benchmark simulated multiple users querying the 314 million row database concurrently. Now, 3 different SQL queries were used. Now, parameters in the queries were randomly generated to ensure the queries produce different responses, just as they would in real-life scenario. Now, with the exception of the full-text query for CrayDB, the SQL syntax was same for both CrayDB and PostgreSQL. A JMeter harness test simulated 30 concurrent users, each connecting to the database and executing the 3 test queries in random sequence and with random query parameters. So each database executed over 4,000 queries during their respective benchmark runs. So these results in this graph show the average duration in milliseconds for each query to process 314 million rows. So CrateDB beats PostgreSQL quite substantially when dealing with selects, aggregations, and grouping. This is because of CrateDB's ability to distribute the workload across an elastic cluster of servers, and so has more CPU cores working in parallel. And this is a unique feature of a distributed system and allows you to scale processing performance horizontally with the addition or removal of nodes. So most SQL databases are not distributed, and so they require you to scale them vertically if you want to increase processing performance. Now, NoSQL databases like MongoDB and Apache Cassandra have pushed database technology beyond the schema, scalability, and performance limitations of traditional relational databases. But proprietary data access interfaces make them harder to learn, use, and integrate than SQL databases, and can sometimes significantly increase the lock-in. So the newest wave of databases, including CrateDB, are distributed SQL databases based on top of NoSQL foundations, like storage, indexing, networking, combining the familiarity of SQL access with the versatility and scalability of NoSQL. So this basically gives you the best of both worlds. Let's take a look at how these two compare against CrateDB. Let's first talk about cluster type and scaling. Both CrateDB and Cassandra have a shared nothing architecture, as opposed to MongoDB, which has a master-slave architecture. CrayDB supports NSI SQL via JDBC, ODBC, REST, and PostgreSQL protocol, as opposed to MongoDB supporting MongoDB query language and Cassandra supporting Cassandra query language. By supporting ANSI SQL, CrayDB makes data management much simpler for mainstream SQL developers, who, by the way, still outnumber NoSQL developers by a 45:1 ratio, according to LinkedIn. While MongoDB supports dynamic schema, Cassandra only supports static schema. CrayDB supports dynamic schema, SQL DDL plus JSON objects, and even arrays of objects. Cassandra supports columnar indexing, unlike MongoDB. CrayDB supports memory-resident columnar indexing. So CrayDB essentially has columnar caches for real-time in-memory SQL performance. What real-time databases do is that they usually require for all the data to fit in the main memory, but that limits how much data you can manage. Our solution for real-time performance without data volume limitations was to implement memory-resident columnar field caches on each node. The caches tell the query engine whether there are records on that node that meet the query criteria and where those records are located. And all of that is performed at in-memory speed. So distributed query performance also contributes to fast query processing and a query planner that makes really smart decisions about which nodes are best suited to perform different aggregations and joins. And speaking of aggregations and joins, CrayDB supports aggregation queries and full joins, whereas neither Cassandra nor MongoDB support this. Finally, we have geospatial queries and full-text search. Both Cassandra and MongoDB have limited support for full-text search and no support for geospatial queries. And CrayDB has Lucene Power support for both of these functionalities. Okay, we talked about a lot of things, a lot of information here. To summarize this, Cassandra and CrayDB both feature columnar indexing, data compression, and eventual consistency, which make them good fits for analytical applications that deliver fast query performance against streams of data or large data volumes. But Cassandra is famously hard to change and optimize as application requirements evolve, while CrayDB is not. And support for data aggregation, text search, joins make CrateDB an easier fit for time series and many other types of use cases. MongoDB tends to be used for more user-interactive transactional applications, and CrateDB is better suited for query and insert-intensive analytical applications. CrateDB also scales more easily and reliably due to its shared nothing architecture versus the Mongo cluster with specialized writable nodes and read-only nodes. If you need schema flexibility, query, versatility, and performance, CrayDB is the better fit. So it's also reiterating on what I said there before, the criteria on which we base the positioning of different databases in the Grand Quadrant is really in the context of IoT applications or digital industries, Industry 4.0. Now we have time series database called InfluxDB. Now, time series application developers often compare CrayDB against single-purpose time series data stores like InfluxDB. So CrayDB and InfluxDB have many important similarities, like both excel at ingesting streams of time series data, both can partition, query, and aggregate timestamp index data in real time, both handle structured and unstructured data, both support data compression, and both are open source. But unlike InfluxDB, CrayDB includes in a size SQL standard access interface. In CrayDB, there's no limit to the number of columns in a table. You can add columns and indexes on the fly without having to dump and reload data. In InfluxDB, the number of columns per series is limited to 200, and the columns by which a series can be indexed and queried are fixed at the table creation time. Now, if you want to add a new tag column, you must redefine and reload the series with the new tag column. And to build richer time series applications, CrayDB supports geospatial queries, full-text search, table joins, subqueries, and user-defined functions. For example, for AI or anomaly detection purposes, which saves you both time and work. Now for performance benchmarking, we use the same data set that we used with the PostgreSQL comparison, 314 million sensor readings, which were stored in CrateDB and InfluxDB, each running on similar hardware. So there were clusters with 24 CPU cores and 48 gigabytes of RAM. Now queries that access data from within a single partition, which are queries 1 and 3 in the graph in front of you, within the same week, both worked fast in both the databases, but faster in InfluxDB. And a query which spanned multiple partitions, which is the query in the middle on your screen, ran 4 times faster in CrateDB. Now, if you take those same queries and run them under load, simulating multiple users querying the database at the same time, the performance of InfluxDB begins to degrade. The average query time gradually increases as users are added to the workload in InfluxDB, and it finally begins hitting a wall at 40 concurrent user mark. Now, reducing the number of concurrent connections to 20 for Influx and CrayDB, a query throughput comparison shows CrayDB processing about 10 times more queries per second than InfluxDB. So in conclusion, CrayDB performed better when answering queries for bigger user bases or when querying bigger data volumes across multiple time partitions. So if you compare time series databases for a project, take into consideration the functional and performance advantages of CrayDB, and also keep in mind that it is also quite specific to the kind of project that you're performing. And with this, I would like to conclude today's session on the grand quadrant of powerful databases. So we talked about the quadrant itself, the criteria that we use to place different databases in their positions, the context to it, the major use cases for time series databases, took also a look at CrayDB and CrayDB on Edge, and finally we closed off with some comparisons and benchmarks between CrayDB and some other popular databases. Now we are in this booming world of data, so why not put it to work to make our lives easier, safer, and better? I look forward to seeing what you do with this. Thank you very much.
Thank you, Tanai. I've seen a couple of questions coming in, so are you okay to take them now? I think we've got a little bit of time.
Sure, let's do it.
Okay, cool. So, first question, can CrateDB run in Kubernetes?
Yes. Yes, in fact, our own cloud offerings run in Kubernetes. So as I said, it makes it really easy for us to scale up and down, create new clusters, all via scripts.
Okay, thank you. The next one, I think I'm just pulling up here. Thanks for the talk. I have to drop out, but I'd like to know, why should I use CrateDB and not another time series database?
Sure. Of course, this was covered in the later part of the webinar where we talked about CrayDB and InfluxDB and the kind of differences between them. But to reiterate what I said, basically, CrayDB gives you the possibility to address your time series use case and also other use cases. And in most projects that we worked on, time series databases are always installed side by side with another database because they can address the time series use cases really well, but not others. And also, if you have industrial use cases like Alpla is one of our customers, and they have a lot of 180 factories around so many different countries, and there's data on billions of bottles. So with CrateDB, you can finally simplify architecture surrounding these kinds of use cases and cover multiple use cases while having a database that is simple to use, it is easy to scale, you can use your SQL knowledge with it. And yeah, I would say, in retrospect, this would be my answer to that. Yeah.
Okay, great, thank you. So there's one more question here. I'm just pulling that up. How can CrateDB support companies with digital transformation initiatives?
That's a really good question. I mean, yeah, especially with the state of the industry, digitalization can be certainly hard, and people in businesses don't want surprises, right? They want to be able to take control and make decisions in real time. So I was yesterday talking with Sid, and we were talking about a report which basically said that around 70% of digital transformation projects fail, 76% of IoT projects fail, 84% of digital transformation projects fail, and about, I think it was 30% fail at the stage of proof of concept. And I'm just pulling up the report right now. Yes, I found it. So it talks about what are the primary root causes of failure, right? And so this is basically a report by Bain and Company, McKinsey and Company, IDC, and Microsoft. I'm sure you can find it on the internet if you look for it, but if you want a specific link, just write to us and I'll send it to you afterwards. So primary root causes of failure in these initiatives. The first one is lack of necessary skills. Second is siloed and resident corporate culture. And third is data and IT infrastructure. So it really says something when, if you talk about top 3 primary root causes of failure, Two are basically people-related reasons, like lack of necessary skills, people need to be trained more, and then resistant corporate culture. And it says something when you have data and IT infrastructure in the top 3 list, which basically means that the databases that we have in the market are quite traditional. So we kind of had 3 ages, so to speak, of databases. So first we had databases which were basically very suited for ERP purposes. Then we had databases very suitable for web purposes like MongoDB, which worked really well on the scale of the web. But then we also had a third generation of databases where there's a lack of competitors, which resulted in how we designed the grand quadrant of powerful IoT databases. And the third age is basically the digital transformation of IoT databases. And CrayDB can help to ensure that you don't have a part of the whole system which breaks down or causes surprise, which means you can reduce your downtime, increase efficiency, and ensure that your business is functioning properly. So as part of digital transformation, CrayDB can help you to move away from listening to people and help you start listening to the data. So CrayDB will essentially remove the bottleneck of volume and scale and help you focus on things that matter the most.
Okay, interesting, thank you. So I have one more question. Are you okay to take that?
Yeah.
We've got time. Okay, do companies other than manufacturers use CrateDB in production? And then there's another part of this. What kind of use cases do they have?
Yeah, interesting. So do companies other than manufacturers? Yes. So we have a couple of other clients like Nokia, we have Bitmovin, and I think you can find a more comprehensive list at crate.io. But off the top of my mind, we also are working with McAfee. So in terms of use cases, other than IoT and sensor data, CrayDB is quite relevant for time series use cases, any other time series use cases where you want to have geospatial analytics or application analytics and are running real-time analytics on streams of network, IT events, and log data. So if we talk about McAfee, like McAfee is one of our customers, and after implementing CrateDB, for example, they reduced their hardware and costs by 75%, which also then emphasizes on how much scalable and efficient CrateDB is. But interesting question. So if you have any specific use case in mind, please write so, and I'll get in touch with you after the webinar and see what we can do for you.
Okay, great. Thank you, Tanai. I think that's all the questions that we can take today just because of time, but we'll be able to follow up, won't we, Tanai, on email if there's any more that come in. So with that, I'd like to close out the session for today. Say thank you to Tanai for the presentation and for answering all the questions. And I'd like to wish you all a great day. Thank you.
Thanks, everyone.